Okay, I'm putting up the quiz question right now. All right, who'd like to start us off with a prayer? Anyone? Anyone? Thanks. Nice and loud.
Dear Heavenly Father, we're grateful that we have this opportunity to come to lecture and learn more about Chapter 2, and we ask that you please bless our minds and be open to the material that's being presented, and that we'll be able to know the right questions to ask. Most of these things in Christ.
Thanks for that prayer. You guys will definitely have questions today. A lot of you will have a lot of questions. So, work. Work is hard because there's lots of variations of problems. So the best strategy is to see a lot of them. From the homework and the videos and the class, you might not see enough for you to get comfortable with the material. So if you need more, go back and do the even problems in the homework. Go get some help. So, but we'll do the best we can. Okay. Take another minute working on this problem. Can someone leave me this mostly drunk bottle of Gatorade in case we get tired? Because it's a really intense lecture. To refuel. Okay, while you're finishing up, I'm just going to do some talking about force in general, or about work in general. So we define work as force times distance. Work, if you want to think about the amount of energy it takes to do something, that's really what we're calculating. Energy in metrics is measured in joules, which is a Newton meter. A Newton, if you're not comfortable in metric, I'll just try to help you out. A Newton is like a pound. So it's a force, it's a weight. It's about between a fourth and a fifth of a pound, if I remember. And so if you push a force of Newton over a meter, you get 1 joule. There's lots of other ways to measure energy. BTUs is a common measure for thermal energy. Foot-pounds is the other metric that we will be using. The other measure, unit we'll be using. So this book weighs about 2 pounds. If I lift it from the floor up 3 feet to put it on the table, how much work did I do? 2 pounds lifted 3 feet, 6 foot-pounds. Okay. If I lift if I lift a 6-pound weight up 1 foot, I've done 6 foot-pounds. If I lift a tenth of a weight up 60 feet, I've done 6 foot-pounds. Okay. You just take the force and multiply by the distance that it takes. Now that's a simple multiplication problem. It's not calculus. It's not calculus because the force is constant. As I'm lifting this up, it still is just 2 pounds. Okay? Although technically no, the further I get it away from the center of the Earth, there's slightly less gravitational force on it, so it does get higher as I lift it up. Right? Not enough to measure, but on Thursday you're actually going to do a problem where it does matter. So do a one in lab. You guys will get to calculate the escape velocity. So how fast do you have to throw something or shoot something for it to never come back to Earth? And that's a calculus problem to figure out how much energy you need, because as you move something further from Earth, it takes less and less force. There's less and less gravitational force between the Earth and the object you're moving, and so it decreases. This is a spring problem. The spring problem, I put the picture up there. It actually has to do with this spring. So if you look up here, the notches are evenly spaced. This is in newtons, so you get 5 newtons, 10 newtons, 15 newtons, 20 newtons, and they're evenly spaced. This is because of Hooke's law. Hooke's law says that the force it takes to hold a spring a certain distance is proportional to the distance. So if after 1 centimeter, if it takes 10 newtons to hold it 1 centimeter, then to hold it 2 centimeters, it's going to take 20 newtons. 3 centimeters, it's going to take 30 newtons. That's what Hooke's law says. It works well for lots of springs. If you pull the spring too far, you change the chemical composition, and then it won't be very springy anymore. So, but for our problems, we assume Hooke's law. Okay. The 2 other kind of problems that we're going to be doing will be like hanging rope and hanging chain problems, where you're pulling up a rope or a chain. The force is not constant. As you pull up the rope or the chain, you get a lot sitting at your feet that you don't have to. It's not hanging off your hands, right? The force feels lighter as you pull it up. Excuse me. Also, we'll do pump problems. Those tend to be the hardest for students. If you've got a tank, as you pump it out, you have weight. Sometimes the weight at any level, or the force at any level of water, changes depending on the depth. Sometimes it doesn't, but the distance that it pumps does change. So you end up with a calculus problem. So, okay, I'm going to stop this. So chime in. You need a little bit more time? So first thing we do with these, with the spring problems, is we have to find our spring constant. So Hooke's law says that the force is proportional to the distance. So here we get K. Oh, that's really bad. K is our constant of proportionality. We're given enough data to calculate what K is. Okay? All right. This is going off. Okay. we know that there's a force of 15 newtons we get when x, which is a distance, is 1.5 centimeters. Am I going to write 1.5 in here? No. You can. You just have to adjust it later. We're going to put everything in meters. If we're after joules, we want Newton. A joule is a Newton meter. So if you're not careful, you're going to be off by several factors of 10. So 0.015. So it's that many meters. So then you solve for K, and 15 divided by 0.015 ends up with 1,000. So the force we feel for this particular spring is 1,000 newtons times the distance in meters. So this is a calculus problem because as I'm pulling on that spring, it gets harder and harder and harder for me, or I have to apply more and more force to hold this spring. Okay? So I can think of chopping this up. If right at the beginning it's hardly any force or no force, and I pull it a millimeter. But now I'm feeling some tension. So I'm at like 1 Newton. And then I pull it another millimeter. So that's like a Newton times 1/1000th of a meter. That is some amount of energy that it took to do that. And then I can pull it another millimeter. So at any point, I can assume for a small distance that it's constant, and then I reevaluate. So you should have visions of Riemann sums in your head, thinking about, this little piece, how much is it? For the next little piece, what's the calculation? For the next little piece, what's the calculation? And each of those calculations is a product. I have a force times a distance. Then I have a new force times a distance. And I have a new force times a distance. And we're adding those up. We will use the integral to add those up for us. I'm going to draw a graph of our situation here. So this is force over here in terms of newtons. Okay, so we're going from this value here, 0.015 meters. At that, I have some force. I can think about moving it a little distance so I can calculate or approximate what that work is. But then I have a new force, and I pull it for a little distance, etc. How far am I going to do that? Over here to 0.05 centimeters, or 0.05 meters, which is 5 centimeters. So I can interpret this integral as the area under the curve, 0.015 to 0.05 under this function. So I can take 1000 x dx. This is my force in newtons. This is my distance in meters. So this is in newtons. This is in meters. And what are my values here? X equals 0.015. What are all of the distances that I'm accumulating, that I'm pulling it or accumulating energy? I go from 0.015 meters to 0.05. Okay. And I can use antiderivatives to find this out because it's continuous over that interval. Antiderivative of 1000x. 1000x squared over 2 from x equals 0.015 to x equals 0.05. And the 1000 over 2 simplifies to 500. And From the upper bound, I get 0.05 squared. 500 times 0.015 squared. And punch that into your calculator. You get something like, is it 375? 325? 375. So what's the answer? B, not diamond. I mean, it is a joule, right? But, you know. I know, it's easy joke. Okay. All right. So, well, questions on the spring, on that spring problem? Questions on the fall problem? Yes?
I just know, like, when we were doing it, like, watching the video for this last thing, instead of doing, like, 1.5 to 0.05, they would do the difference between 2 and 0 to the difference between,
So just doing the, you mean the difference of the bounds? So like in that case, it would be like 0.0, yeah. So the actual values that you're at, the actual x values are what's important here. So it's not, you shouldn't do just the difference, like 0 to 0.5. If you're pulling it from the natural length itself to like 5 centimeters, so basically x equals 0 to 5, then that makes sense. Or sometimes they'll give you the length of the, they'll say that the length of the spring is 5 centimeters, and you're pulling from 5 to 7. Then you would have to subtract 5 off, right? Was that the kind of problem it was in? Yeah. So, okay. Good question. Other questions? Yes. I don't know off the top of my head which one was number 3. We're gonna do a hanging rope problem, something like the hanging rope problem, something like a pump problem. So is it like one of those?
It gave us the first thing, it gave us joules instead of newtons.
Okay, so we can talk about how to do that. So, so joules, you know the amount of energy out, right? So if it tells you it takes this many joules, you know the amount of energy. How they figure that out, I don't know. You can, using some pretty cool fancy tricks, to figure out how much energy it takes. So that means you know, do you remember how many joules it said?
5 joules.
So if you get 5 joules, that's the answer to your integral already. That's the answer to your sum. You don't know the spring constant. Okay? So your unknown, you still have an unknown here, but you do know your bounds. And so you can put in your bounds and end up solving for k. In that, because it'll tell you, like it takes 5 joules to move from 2 centimeters to 5 centimeters, or 3 centimeters to 4 centimeters, something like that. So then you can put your bounds in here in terms of meters, and then actually calculate your k after you do the antiderivative. So you end up with the constant in there. So you're going to have like a k x squared over 2 equals 5. And you get some bounds from bound 1 to bound 2. And the only unknown in there is going to be a k. And so that's the way you solve your k in that situation. If they give you the work, then that's what you need to do. Yes?
Just a sign that it's not any of the next thing, explain it.
Yes. Thank you very much. I should have mentioned that earlier. Yeah, one of the reasons why we have you do the WebAssign before is they've got a lot of nice resources for you. And one of them is the videos. So you can click on the watch this and they have someone walking through a similar problem. So thanks. Okay. So during homecoming week, I actually don't know if they still do this, but they hang a giant, they used to, on the Tanner building, hang a giant BYU flag, a really big Y. Has anyone ever seen that? Wow. I mean, I know a lot of you are true freshmen. You haven't been to, it hasn't been homecoming week yet. But I'm not sure since they put the new addition on if they still do it, the new addition to the Tanner building. It's a really big flag. I don't know how much it weighs. I'm going to assume a ton, but like literally a ton. So we're going to calculate how much energy it takes to pull that flag up. So the flag looks something like this, okay, hanging off the top of the Tanner building. I don't know exact values, but we're going to say that this is 160 feet high. We're going to say the flag is 100 feet long. Okay, and we're going to say that the flag weighs 20 pounds per foot. Okay, so 20 pounds per foot. So like if you just took the bottom foot of the flag and chopped it off, that much would weigh 20 pounds. Okay, I don't know what it really weighs, but we'll try. So before we do this, I'm going to write down 4 steps that you can use for any of these work problems. Okay, hopefully it'll make it easier for you. It might not, but hopefully. So the first thing we're going to do, number 1, is you're going to put on a scale. And that means like, where is x equals 0? And where is x as a distance? Okay. So in our case, I could choose, I'm trying to choose a different color here. I have different places where I could choose x equals 0. Do I make x equals 0 the top of the building? Do I make x equals 0 the bottom of the flag? Do I make x equals 0 the bottom of the building? Any of those are kind of natural places. It actually doesn't matter where you put your x equals 0 or y equals 0. If you like using y's when you go up and down, that's great. I just tend to use x's. But we need to put our x equals 0 somewhere. We're going to set a scale. Let's start with x equals 0 at the top. So I'm going to cross these out. And let's do x equals 0 here. And this is x equals... And here I could choose to make this a positive 100 or a negative 100. I'm just going to keep it as a positive 100. Okay? So here's x equals 100. This would be x equals 160. Now, the answer you get will be the same no matter where you put your x equals 0, no matter how you set up your scale. Okay? But the important thing is when you put your scale there, you have to be true to your scale through the whole problem. Okay? And use those values. All right, so step number 2 is we're going to chop it up. Into small pieces. It's a positive 100. It doesn't matter. In this case, if I had something above here, then those values would be negative. Which sometimes happens in pump problems. You might have x equals 0 at the top of your tank. You might have x equals 3 at the bottom of your tank, but you're pumping it out 1 meter above. That would be x equals a negative 1. So we're going to chop this up into small pieces. I'm going to look at it from the side view here. So here's the building, here's the flag, like this. I can think of chopping up that flag into lots of little pieces. Okay? And thinking about each of those pieces, figuring out how much energy it takes to lift those pieces. And that's gets to number 3, is calculate the amount of work for an arbitrary piece. I before E, except after C. Is that right? Piece. Except sounding an A is a neighbor's away. Neighbors, no. Yeah, and I'll throw out me. That's right. Nice job. Good job. Go Brian Regan. Okay, so with my scale, I have x equals 0 here. I have x equals 100 here. Whereas x is a distance, I didn't do that in my very first step. X is a distance is now my distance down. This much is an x. So this value, this is x as a distance, this is x as a coordinate, or a place. Okay? And delta x is a little piece at the end of my x. Okay? So for this little piece right in here, if x is right there, if delta x is that distance, then to your neighbor, tell me how much energy it would take to move this little piece up to the top. Okay? So work with your neighbor, see if you can tell me how much energy it would take to move that little piece up to the top. How would you calculate that? All right. Let's start off with just the distance. With the way that we set up our scale, we have to pay attention to our scale to answer these questions. Okay? With the way we set up the scale, how far is that piece going to move? X. It will move X. It will move. I have to take it from this place here all the way up. Okay? That's a distance of X. If I set up my scale differently, it would be different. If I set x equals 0 here, and this is x equals 100, then x would be the distance up. Then what would the distance be for that piece right here? How far would it travel? What's the distance it needs to travel? It would be 100 minus x. I have 100 feet from here up to there. If this much is x, then how much do I have left? Then I have 100 minus x. Okay? So depending on your scale, your distance might be x, your distance might be 100 minus x, it might be x plus 1, it might be x plus 100. Just depends. Okay? But we have to be true to our scale when we first set it up. Okay? So our distance, work is a force times a distance. We know our distance is x. How about our force? In this situation, what is our force? And force, you're thinking about weight, right? Yes. Be the what? Not the rate of falling. Okay? We will get into the gravitational force and acceleration in a minute. Here, let me go back here. Yes. Great. So we have to use kind of the density of the flag here to know how much that weight will be for a delta x slice. So delta x is in terms of feet. So if I have a 1 foot cut off, if delta x is 1, then I'm going to have 20 pounds, because 1 foot times 20 pounds per foot gives me 1. If it's a half a foot, then I get 10 pounds. If it's a tenth of a foot, then I get 2 pounds. Okay? So our force is going to be 20 times, times delta x. Okay? So this is a force. This is now in pounds, because I have a pounds per foot times a foot. and this is in feet. It's a distance. So now I know how to calculate for any arbitrary x. For any x value and any little change from that x value, I can calculate that. And hopefully that's enough for me to set up my integral. Because in the limit, my delta x will become dx. So I'm going to have 20 times x dx. Because my 20 times dx, those are the two pieces there. My x right there. Now, what are the bounds? Talk to your neighbors. 10 seconds. What would the bounds be? All right. Okay, what's my lower bound? 0. What's my upper bound? 100. Those are all of the places on the flag. Excuse me. Those are all of the places where the flag overlaps my scale. Excuse me again. Those are all of the places where I've chopped up on my x scale where I have pieces of flag that I need to lift to the top. If I wanted to lift up just the top half of the flag, well, it doesn't make a lot of sense. But okay, we're not going to go into that right now. Okay, but again, we're true to our scale. If we had chosen to make x equals 0 the bottom of the building, if we had chosen to make x equals 0 the bottom of the building, then our scale would be different. If this is the bottom of the building at x equals 0, and we made the top x equals 160, then what value would this be right here at the bottom of this? That would be 60. So what would our bounds be? 60 to 160. Okay, our function would be different, our integrand would be different here, but the bounds, yeah, and the bounds would also be. We'd still get the same value, but we have to be true to our scale. Okay, we're not going to go through and actually calculate how much energy that is right now.
The question about that, does it end in foot pounds like for units?
Yes. In fact, you should use the units to help make sure you set this up correctly, because dx is a distance set up in feet, and this is in pounds. That's a force in pounds. Oh, we were actually thinking about it a different way, right? Okay, erase, undo. There's another way to think about it, but we haven't talked about it that way. Okay. We thought about it in terms of this piece was in pounds, right? Because you had 20 was a rate. It's pounds per foot. The dx is in feet. It's a distance that we've measured in feet. And then x here, that's in feet. So we end up with pounds times feet. So if in any piece we get pounds times feet, when we add them together, we get pounds times feet. Okay?
Integrand doesn't change that? It's not like pounds per feet squared?
No. So that's one reason why this dx is so important. Because if you ignore the dx, you're in trouble with your units. But if you think of what we did with large pieces, it's the integral just adds those up into small. It just takes smaller pieces, but it still adds them up in the same way. If we chopped up that, we could get a pretty good approximation by chopping up that flag just into 1 foot widths. And we would take each of those widths, calculate the weight, figure out how far it'd have to travel. We could do that multiplication. We do that multiplication 100 times and then add up all those values. Each of those products would be a foot-pound. And so in our integrand, we need foot-pounds. We need that dx to make sure we get foot-pounds. So great question. Other questions? Yes. With the way that we set it up, so with the way that with our scale, then it's just x. But if you made x equals 0 at the bottom, then, like with the green over here, then the distance that it would travel would be 100 minus x. So,
When you started x equals 1, you're thinking about 99 being flat.
oh, you're thinking about it a different way. So, yeah. So you're thinking of it as, yeah. There's two ways to think about them. Both of them work. Okay. So the way I thought about it was I thought about doing the thought experiment. I'm chopping it up into 100 pieces or 1,000 pieces, however many pieces, and I'm just looking at raising each one of those up. That's different than thinking about it with the weight that you feel. Right? If I start pulling up right at the very beginning, I've got 2,000 pounds. I've got 2,000 pounds hanging off. Right? I know you guys don't think I can lift 2,000 pounds. All right, so I've got 2,000 pounds, and then I lift that 2,000 pounds, and I get a foot up there. Now I have a little less. Right? That's the way you're thinking about it, right?
I was confused because when I got to the 100 minus x, but if you do that integral,
That's right. That's right. You can think about it either way. So to think about it that way, I still have 100 feet here. I'm picking x as the distance down. So this distance is x. This is x equals 0. But that x represents how much I've pulled up so far. So the weight that you feel at any point is what's left hanging over the top. So the weight that you feel is 100 minus x times your 20 pounds per foot. And how far do you move that? This is where it's a little tricky. Do I move that whole thing all the way to the top? Not at that force. I just move it delta x. I just move it a little bit, and then it gets a little lighter. And then I move it a little bit, and it gets a little lighter. So here, this is my force, and delta x is my distance. And yeah, you'll end up with the exact same thing. If we had just switched our scale and made x equals 0 at the bottom and x equals 100 at the top, we would end up with the exact same integral that ends up with. Basically what you've done is, one way you end up with finding the area under that curve, and the other way you end up finding the area under that curve, and they're the exact same area. So, nice. Okay, let's move on to the next problem, the pump problem. Okay, so this is a hemispherical tank. We're pumping the water out. Okay. The amount of energy it takes to pump it out, we're going to think about in slices. So we're going to actually use the same process as we did the last time. It's a little more complicated to calculate the force for these. But we're still going to do the same thing. What the first thing we do is put on a scale. Then chop it up. Then calculate the work for an arbitrary slice or an arbitrary x. We're going to be pumping it out 1 meter above the top of the tank. So, good question. And 4, we're going to use 3 to set up the integral. So there's 3 particular places we could put x equals 0 here. 3 natural places where we could set up our scale. Where do you guys want to do it? The top, where we pump it out at, up here. The top of the tank right there. Or the bottom of the tank right there. Should we take a vote? Just kidding. Who wants bottom? Snap if you want bottom. Snap if you want the top of the tank. Snap if you want the very top where the water comes out. We'll just do bottom. Okay. They were kind of evenly split between those others. Okay. So I'm going to set up my scale. And this is going to be x equals 0. This will be x equals 3. Because this distance down is 3. Because it's a hemisphere. And this will be x equals 4. But again, you can make the top, we could make x equals 0 right here. You could make this x equals 3 right here, and you could make this x equals a minus 1. Or you could make it x equals a minus 3 and the top x equals 1. As long as you're true to your scale, you'll be okay. So we're not going to do that one on this particular problem. So we're going to chop it up. How should I chop this up? Vertically or horizontally? What should my slices look like? Horizontally. I can think about, I want to turn this into my book problem. Okay, I want to think about lifting a book 3 feet. Okay, I'm going to think about taking an arbitrary slice here, figuring out how much work it takes, and the work that I'm doing here is the work against gravity. So I'm looking at each slice. I can easily think about each slice as a disk, calculate how much weight, how much force there is in that disk, like the weight of that disk, and then move it, figure out how far that disk has to move up to get out of the tank. Okay. So if this is x equals 0, x is the distance up. So we're going, x is this distance right here. It helps a lot to think about x as a distance in each of these problems. Okay? So to calculate the weight of that disk here, I need to figure out what the volume is, and then I need to turn that volume into a weight. If we're dealing with water, every meter cubed is 1,000 kilograms. So 1,000 kilograms per meter cubed is the density of water. Okay. That's not coincidence that it's that. They tried to make a kilogram, 10 centimeters times 10 centimeters takes 10 centimeter cube. They took the amount of water to fill that cube and called it a kilogram. So, not coincidental. Okay. At least from what I heard. Some of you might know better than me. Okay. So I need to figure out what that volume is. I'm going to start with trying to calculate the volume of that disk. But the volume, to calculate the volume, I need the circle times the area of the circle times the dx. The area of the disk, I should say. And I need the radius of that circle first. So how am I going to figure that out? Well, if I draw that line, I'm just going to use some geometry here. You can also put this on a grid and use your equation for a circle or for the lower half of a circle. You can do it that way too. I tend to just use geometry. So the radius there is 3. I need to figure out what this distance is. What is that distance? 3 minus x. I have 3 from the top all the way down to the bottom. I have x as the distance from the bottom up to a given value, whatever x is. What I have left is 3 minus x. Okay? So now I can use the Pythagorean Theorem to figure out what this length is. So that length is going to be the radius squared minus 3 minus x squared square root. That's what that length is. Questions on how I got that length? Okay. So I want the volume of that slice. So the volume will be the area, which will be pi times the radius squared, 3 squared minus 3 minus x squared, quantity squared, times my delta x. So that's the volume. How do I turn that volume into kilograms? I'm going to turn it into kilograms. As I just need the volume times this density. So 1,000 kilograms per meter cubed times pi times 3 squared minus 3 minus x quantity squared. My squareds and my square roots cancel out there. Times delta x. There, I'm good with kilograms. But is kilograms a force? Kilograms is not a force. Kilograms tells you the mass. Force is mass times acceleration. So here we kind of equate on the surface of the earth when we weigh things. We say it's this many kilograms or this many pounds. That's actually not correct, or can be misleading, because if you go to the moon and weigh yourself, your mass hasn't changed, but your weight has. Okay? The force between you and the moon, which is your weight, is only about 1/6 of what it is when you're here on Earth, when you're standing on a scale. But mass is the amount of stuff you're made out of. That's still the same. So to turn kilograms or mass into a force, what do we have to do? You have to multiply by the acceleration due to gravity. So we need a mass times acceleration. So I haven't had one physics class in my life. So when I was sitting in your shoes, all this was like new to me. So some of you might be having that experience too. So 9.8 meters per second squared. That's the acceleration due to gravity. Times 1,000 kilograms per meter cubed times pi times that thing times delta x. Now I have a force. I just have to multiply that times the distance. Then I have my work, and let's use the integral to add all those up. So these first three terms are just constants. I should have given myself a little more room. 9.8 times 1,000 times pi. Didn't get the units in there. And then 3 squared minus 3 minus x quantity squared. So I have to multiply by the distance that it travels. How far does each slice travel? 3 minus x. So the distance from this slice... Oh, no, I made a mistake. Yeah. So with this setup, it's 4 minus x, because I have to do 3 minus x plus 1 more. Or I can think about over here, this whole distance is 4, and I've gone up an x. So the rest of the distance is going to be 4 minus x. Okay, so I need 4 minus x here. No, like just this distance. This distance that distance is like the force times distance that we're taking. The rest of all this other calculation, all these other things, that gives me my force. So I have my force times my distance. Okay. And what would my bounds be? So you have to be true to your scale here. So go back to what's your scale. If you set up your scale differently, you might have different bounds. So our bounds really fast. What are all of the x values where I'm pumping water out? From 0 all the way up to 3. So x equals 0 to x equals 3. So x equals 0 to x equals 3. All right. So there's a question over here. Any other questions? Oh, great question. Why would the bounce not be to 4? We're not accumulating water. We're not pumping out any water from x equals 3 to x equals 4. Or you can imagine if we had a tank where it was just maybe up 1 meter, water was up 1 meter, and everything else was the same, we would only be pumping up from x equals 0 to x equals 1. Oops, x equals 0 to x equals 1. Because those are the only places where we're pumping water out. Okay, have a great day. Sure. And I'll get these up soon.
Thank you.
You're welcome. Thank you. You're welcome. Have a great day.
Yeah, I mean, in some ways it's good because